Alright, so first we have a box where the length is twice the width, and this is the bases of the box. We know the surface area. Okay, let's draw a box. Here's a box. Okay. So if we look at what we have, the length is twice the width. Well, if this is x, let's say this is 2x, okay? We don't know the height, so let's just call it h. So surface area, so each base is 2x squared because 2x times x is 2x squared, and there's two of those, top and bottom, so that's 4x squared. Then you also have all these sides coming up around, all four going around if you picture like it's on the ground and there's the four upright sides. And the area of all those is, well, actually, you know what, in this case they're different, right? Because this one is xh, this one is xh. So we have plus xh plus xh. And we also have this side in front, which is 2xh. And then we have the one in the back, which is also 2xh. So then our surface area is 4x squared plus, let's see, 1, 2, 3, 4, 5, 6xh. And then right about here is where you're like, wait, what are we doing? Oh, we know the surface area is 300. So 4x squared plus 6xh equals 300. So that's our constraint, or like the information we have. What are we trying to do? Well, we want to produce a box of maximum volume. So let's see, the volume of this box is going to be 2x times x, that's the area of the base, times the height. So this is 2x squared h. So now we need to solve for one of the variables. Let's solve for h. So if we subtract 4x squared, we have a 6xh equals 300 minus 4x squared over 6x. So h equals 300 minus 4x squared over 6x. So then, and I'm gonna move this out of the way. Maybe just move this to a new page. We'll deal with this in a second. Sorry. All right. So if that's our h, now I'm going to put it back in here. So volume is 2x squared times 300 minus 4x squared over 6x, okay? Because we're just, here's our h, and we're replacing it for that h. So now this is 2x squared over 1, just to keep everything lined up. If we want to simplify, we have an x squared over an x, so that's just a single x on top. 2 over 6 simplifies to 1 over 3. So we end up with x times 300 minus 4x squared over 3, which is 300x minus 4x cubed over 3. So then our volume is then 300 over 3 is 100. X minus 4/3 x cubed. Okay, that's finally our volume. So now we'll differentiate. And we get 100 minus 4x squared, set it equal to 0. 100 equals 4x squared. So then 25 equals x squared. And x equals 5. So there's our critical point. Now the question, of course, is, is that what we want? Well, second derivative of the volume is going to be negative 8x. So add x equals 5. That's going to be negative. So that's a maximum. What were we trying to find? Oh, good. We were trying to maximize volume, so we're okay. So then we look at that, we know that the base of our box, if x is 5, this is 5, this is 10, and then our height, well, our height was this right here. So if we do 300 minus 4 times 5 squared over 6 times 5, that's 200 over 30, which is 20 over 3, which is about 6.667. So then our dimensions, and I think I made it so any order works in the ABA, but it's 10 by 5 by 6.667. For the next one, before we even deal with all the prompts and the answers, let's just look at what our question was. We want two positive numbers that the sum of first and twice the second is 64 and the product is a maximum. So our constraint is like the numbers we have. So we have two positive numbers, sum of first plus twice the second. So let's say a plus 2b equals 64. Again, this is our constraint because it has a number in it. Like it's actually equal to something. Versus what we're optimizing, that's the product. So that's just product equals AB. That's where we really don't have a whole lot of information. So that's what we want to optimize. Now I'm going to kind of look here and I'm like, oh, well, I see I have X's and Y's there. So I'm going to rewrite with X's and Y's just so I can like be consistent here. Normally it wouldn't matter, right? So that's XY and X plus 2Y. Okay. And if you'll notice, like the only options we have, like there isn't like a y plus 2x. It's like messing with you. There's only one that ends up working. Okay, so x plus 2y ends up being our constraint. Our equation to optimize written with two variables is p equals xy. Now we want to write in terms of a single variable. So if we solve for x, and that is kind of the simplest thing to solve for, x equals 64 minus 2y. So then our product would be 64 minus 2y times y. And that's not an option. I didn't show you all the possible answers, but that's not an option. So what if we solve for y instead? Then we would have 64 minus x over 2, which is 32 minus 1/2 x. And so then our product would be x times 32 minus 1/2 x. And that's an option, so that's what we're optimizing. And as far as the numbers we're finding, these all kind of work. I sort of made it that way. So now let's actually solve the problem. And so if we do that, this is what we're working with. So let's multiply it through and we get 32x minus 1/2 x squared. So then p prime is 32 minus x equals 0. So x is 32. Probably our answer, but let's check. Second derivative is -1. So that has to be a maximum, which is good because you're trying to maximize. So that means our numbers are 32. And then y is 32 minus 1/2 x. So 32 minus half of 32 is 32 minus 16, which is 16. So then our numbers are 32 and 16.